Hey everyone, welcome back to Calculus 3. This will be lecture 18 of the course. And in this section, we're going to talk about tangent planes and normal lines. So we certainly talked about, towards the earlier sections of the course, we discussed lines and planes in space and just talked through how we can derive some of those the equations for some of these things. We want to revisit this now after having gone through a lot of the stuff that we recently waded through, gradients in particular, and also partial derivatives. And we want to revisit this and expand our capability to being able to identify tangent planes in particular, kind of the big thing. So normal lines, let's start with normal lines. Well, let's jump into it here. So this will be section 3.7, tangent planes and normal lines. Okay, and so let's start with the idea of normal lines. And I think people probably have a good sense of what a normal line is, but just how deeply ingrained in the geometry of space normal lines are may be somewhat unknown to people, right? So we've certainly talked about normal lines in the 2D world, but in the 3D world of surfaces and solids, normal lines have just as important a role. So let's consider the case of like the billiard ball example, right? So say you've got a billiard ball that's in motion, right? It's in motion, along a certain line, right? And let's say there's another billiard ball at rest that is precisely in the line of motion here. So this is the line of motion. Okay, and so this ball is obviously precisely in line with this other one that's at rest. And so when these two collide, what's going to happen? Well, the two will collide. And you can imagine this plane between the two right at the point of impact, right? So these two balls will touch, in theory, at a single precise point. And when they impact, there'll be what's called a line of impact. In this case, in the case that I've drawn, the line of impact is perfectly in line with the line of motion, right? So what will end up happening here is that if the ball is indeed moving along this line of impact, when it strikes this other ball, it'll stop dead and it'll transfer all of its momentum to the stationary ball. Right? So in this case, this ball is in motion. It'll stop dead and transfer all of its momentum to this other ball, which will, obviously move away along the same line of motion. Okay, so this is the case where the balls are perfectly aligned. Now, what happens in the case where you've got the same sort of situation? You've got a ball moving in a particular line of motion here, but then you've got a ball at rest a little bit outside of the line of motion, right? So you can see where this is not going to strike this ball at precisely in a straight line. All right, so what's going to happen there is when the two collide, when the two balls collide, they're going to collide on a surface like this, which is not in line with the line of motion, right? So if the ball is not moving along this line of impact, it's going to end up being deflected, right, to one side or another, right? So this guy's going to end up going this way, and this one's going to end up going this other direction, right? So in this case, part of the ball's momentum is going to be retained, and part of it will be transferred to this other ball, right? So you'll have this guy moving off in this direction, and you'll have the other one moving off in this other direction. Okay, and so why do we bring this up? Well, the reason to bring this up is that this line of impact is called the normal line to the surface of the ball at the point of impact, right? So in this case here, it's just the easiest case to see, right? This is the line that is, you can think of this line as the surface that touches this ball at rest at just one point precisely. And that's also the surface where the impacting ball touches, right? And then so the line of impact is then normal, right? It's at a 45-degree angle. It's perpendicular to that line of impact. Okay. And similarly down here, the momentum is transferred into this other ball along the line of impact, which is normal to the surface where the two touch, right? And so the whole reason to bring this up is that is just to see how deeply ingrained this idea of normal lines and tangent surfaces are in the 3D world of like these solid objects. Okay. Okay, so that's just kind of like a little bit of motivation, and we'll get into, how do we identify the equations of surfaces like these and of normal lines like these. So, as part of finding a normal line to a surface, we've seen that we can also solve the problem of finding a tangent plane to a surface, right? So this is kind of all wind up still, right? So previously when we talked about finding the normal line, right, when finding the normal line to a surface, we can also, kind of enabled us to solve the problem of finding a tangent plane to the surface. Okay, so let's talk through some of that. So let's let S be a surface, and specifically a surface given by the equation f of x, y, z equals 0, right? So this surface f of x, y, z equals 0, and we'll let p x naught, y naught, z naught be a point on S. Okay, so this is some point on S. And let's also let C be a curve. And this C is going to be a curve on the surface S that goes through P. Okay. And this curve C is going to be defined by a vector valued function Okay, so this is a vector valued function. R of t equals x of t I plus y of t j plus z of t k. Okay. All right. So we've got S, a surface given by this equation. P is a point on the surface. And C is a curve on the surface going through P, and it's got this curve C has this vector valued function that defines it. Okay? All right, so that's kind of the wind up. Now, what we can say then is for all t, right, then for all t, f of xt, comma, yt, comma, zt equals 0, right? That's obvious. F of x, y, z is equal to 0, so obviously if you plug in something specific, you get 0 as well. If f is differentiable, and x prime of t, y prime of t, and z prime of t all exist, then it follows right, then it follows that, this is just going to be basically the chain rule. It follows that 0 is equal to the derivative of f, okay, which will be equal to, and this is just the derivative, the chain rule being applied here. So you got the partial times the derivative of x plus the partial of y times the derivative of y plus the partial with respect to z times the derivative of z. Okay, so that's just the chain rule. Okay, and then for this expression, you could, if you think about what this is basically, you can think of so these partials, right? Partial of x plus partial of y plus partial of z. This taken times the I vector times the j vector times the k vector, that's going to be just the gradient, isn't it? Right? And then this other piece, x prime plus y prime plus z prime, that's going to be basically the derivative of the vector valued function that defines the curve C. Right? So an alternative way to write this would be to write this using the gradient like so. Right, and I'm at a specific point, right? So we're kind of making that jump here too. At a specific point, x naught, y naught, z naught, right? At a specific point, then this is all equal to, this is the gradient dotted against is the dot product with the derivative of the r function. R being the function that defines the curve on the surface. Okay. All right, so let's write that in. This is the gradient. And this, what is the, so if C is a curve and it's defined by r of t, then this is going to be the tangent vector. Right, remember we've plugged in a specific x naught, y naught, z naught here. Okay. And so what does this tell us? What is this telling us then? So hold on. So let's write this out one more time. X naught, y naught, z naught dot r prime of t equals 0. What does that tell us? This means that the gradient at P, right? The gradient at the point P is orthogonal to the tangent vector of every single curve on S that happens to go through P. Right? The dot product being 0 means that these two are orthogonal. Right? So this is a specific point P. The gradient at that specific point is going to be orthogonal to the tangent vector of any curve on S through P. Right? So basically all tangent lines at S seem to appear to lie in a plane that is normal to this guy here. Okay. All right, so that can be kind of a tricky thing to visualize. Let's lay out a more precise definition and then do some examples to see what this is all about, what this looks like. Okay, so let f, we're using big F here. Let big F be differentiable at the point P x naught, y naught, z naught on the surface S given by the function or the equation f of x, y, z equals 0, such that the gradient at x naught, y naught, z naught of f is non-zero. Right, it's not equal to the 0 vector. Right, so f is some differentiable function at the point P x naught, y naught, z naught on the surface S given by f such that the gradient is non-zero. Okay, then two things follow. Right, the plane through P, the point P, that is normal to the gradient of f x naught, y naught, z naught, is called the tangent plane. Okay, it's called the tangent plane, and then I guess technically to the surface S at the point P. Right, so you've got this point P on this surface, and you've got this tangent plane relative to that point. Okay, and that's basically what S is. Okay. And then secondly, the line through P, having the direction of, and then the direction, of course, is given by the gradient as well. This is called the normal line to S at P. Okay. Right, so this is a very extremely wordy definition. Let's talk it through. So let f be differentiable at the point P on the surface S, and then f is given by, f equals x, y, z equals 0, such that the gradient evaluated at x naught, y naught, 0, or z naught is non-zero. It's not equal to the 0 vector. Now, if this is true, then the plane through P that is normal to this vector, gradient vector, evaluated specifically at x naught, y naught, z naught, this plane is called the tangent plane to S at P. Okay, and the line through P having the direction of the gradient at that point is called the normal line to S at P. Okay. Okay. Right. So this is all. Hopefully this is. Some of the wording can be a little convoluted, but what we're really talking about here is a tangent plane to a surface, right? So if you've got some, just like when we had a tangent line to a curve, we know what that means. Extend that intuition to surfaces and planes, right? So you can have a plane that touches a surface at just one point, and that's what we mean by the tangent plane. And the normal line to a surface has basically the same extension. The normal line to a curve is a certain thing. It's basically the line that is orthogonal to the tangent line, and that's the same situation here. Okay, so what can we do with this? Well, one of the things that we'll obviously want to be able to do is find an equation for the tangent plane. Okay, and so how do we do that? Well, to find an equation for the tangent plane to S, right, at a particular point, x naught, y naught, z naught, right? So to find an equation for this guy, we need to let basically your x, y, z be an arbitrary point. Right, let that be an arbitrary point in the tangent plane. Then what do you have? Well, you've got this equation that we've seen before. V equals x minus x naught times I plus y minus y naught times j plus z minus z naught times k. So this is obviously going to lie in the tangent plane, right? Because x naught, y naught, z naught's in the tangent plane. X, y, z is an arbitrary point also in the tangent plane. So this vector is going to be in the tangent plane. Right, and we've seen this before. Now because, right, here's the trick part. Because the gradient of f at x naught, y naught, z naught is normal to the tangent plane, right? It's normal to the tangent plane at this point. Okay. It must be orthogonal, basically, to everything in the tangent plane, right? Right? Because this guy is normal to the tangent plane, it's going to be orthogonal, obviously, to everything in the tangent plane. Okay. And what does that mean? Well, therefore, basically the gradient vector, that vector evaluated at x naught, y naught, z naught, and dotted against any vector v that's in the tangent plane is going to be equal to 0. Right? That's just the dot product telling us that. And this is going to lead to the following theorem, which will tell us how to identify the equation of a tangent plane. Okay, so this leads to theorem. Okay, so this theorem. So if f is differentiable at x naught, y naught, z naught, then an equation of the tangent plane, an equation of the tangent plane to the surface given by f of, and this is just the equation, x, y, z equals 0 at this particular point, x naught, y naught, z naught is, right, and so here's the form of the equation. It's just going to be the partial of f with respect to x evaluated at x naught, y naught, z naught times x minus x naught plus the partial of f with respect to y evaluated at x naught, y naught, z naught times y minus y naught, and plus the partial with respect to z evaluated at x naught, y naught, z naught times z minus z naught equals 0. This will give you the equation. This is an equation for the surface. For the tangent plane to the surface given, right? So at this particular point, right? So you've got this surface, and you've got this point on the surface, x naught, y naught, z naught. You want to know the equation of the tangent plane at that point? This will tell you. This is an equation of that tangent plane. There are others, of course, right? But this is one way to find it. One way to find an equation. Okay, all right. Let's do an example. Okay, so example. Find an equation. Find an equation of the tangent plane to the hyperboloid given by, all right, and here's the expression or the equation, z squared minus 2x squared minus 2y squared equals 12. Okay, and so we want to find the equation of the tangent plane to the hyperboloid given by this equation at the point, right? You're always going to need a specific point if you're looking for a tangent plane, because depending on what point you're talking about, the tangent plane will obviously vary. So at the point 1, -1, 4. Okay, and so that is so that's the first example. So a hyperboloid, right? Remember, a hyperboloid is kind of like it kind of looks like this. I mean, this is just like some kind of a generalization of it, but it'll vary obviously depending on the equation. But you've got your x, y, and z. It's kind of looks something like this. And so for a hyperboloid, something like this, what we're basically given is some point on the surface, right? So maybe it's right here, for example. And what we're asked to identify is that there's going to be a plane that could be characterized as tangent to the hyperboloid at just this point, right? Which means this plane touches just this point, touches the surface at just this one point. Right? It doesn't precisely mean that, but you can use that as an intuitive sort of way to think about it. And what we want to know is what's the equation of that surface, right? What is the equation of this tangent plane? Okay, and so that's exactly what the previous theorem taught us how to do, right? We need the three partial derivatives, and then it's just we need to evaluate the three partial derivatives, and then we just need to plug it into this form. Okay, so we'll start with the partial derivatives. So f differentiate with respect to x is going to be equal to, just looking at this, it's going to be equal to negative 4x. And f with respect to y is going to be equal to negative 4y. And f differentiated with respect to z is going to be 2z. Okay. And so those are the partial derivatives. Now, it is, I kind of skipped this step, but it is important to notice that when we're talking about the partial derivatives, what we're differentiating is this, right? This part of it, f of x, y, z equals 0. You want to differentiate this side of it, right? So we're looking at z squared minus 2x squared minus 2y squared minus 12 equals 0. So we have to differentiate this thing. So in this specific example, it doesn't really matter, right, whether we bring the 12 over or not, because it's just a constant and it disappears in all of the partial derivatives. But technically speaking, this is the part that we want to take the partial derivatives of. We want to identify the partial derivatives for this piece over here. So we have to wrap the 12 into the function here, right? Because this is specifically f of x, y, z. Okay, so just a side note there, right? So now we know the partial derivatives. Can we evaluate them at the point of interest? So at the point, what's the point? 1, negative 1, 4. So you've got f of x of 1, negative 1, 4. You've got f of y at 1, negative 1, 4. And you've got f sub z at 1, negative 1, 4, right? We need each of those. Well, these are really simple functions, right? So this is just going to be negative 4. This one will also, well, this one will be positive 4, actually. And then f sub z is going to be 2 times 4, so it's going to be 8. Okay, so we've got those pieces. And so we can just plug this into the expression. Now, I won't rewrite the equation. I'll just show it to you and point at it. It's on the other side of this page. It's this guy here, right? Right, so here, this is just the partial, del f, del x. This is the partial, del f, del y. And that's the partial, del f, del z. Right, this other part is just x minus x naught, y minus y naught, z minus z naught. So this looks like a big convoluted mess, but this is actually fairly easy. It's just partial times x minus x naught, partial times y minus y naught. So this is really easy to use, and we can just plug in the numbers that we found here. And so what do we get? Well, we get negative 4, and then it's x minus x naught. X naught is 1, so x minus 1 plus, and then it's positive 4 right there, y minus y naught. So y naught is negative 1, so this would be y minus negative 1, so y plus 1. And then plus the partial with respect to z, and that's 8, and then it's z minus z naught, and z naught is 4, so this would be z minus 4, and then that's all equal to 0. Right? And so this is the equation. Okay, and of course you could simplify this. You could do a lot of work to this to make this, a nicer. You could, expand this, consolidate some of the terms, and maybe even, simplify some of the terms as well. But this is the basic setup. Okay, right, and again, this is the equation of the surface in this terrible picture that is tangent to this hyperboloid that we're given, the equation for this hyperboloid, and this point on the hyperboloid. This is the equation for the tangent plane to this hyperboloid. Okay, excellent. All right, how about another example? Let's find the equation. Find the equation of the tangent plane to the paraboloid. And it's going to be written like this: z equals 1 minus 1/10 x squared plus 4y squared. Okay, and so this is the one way to write the equation of the paraboloid. All right, this is not in the f of x, y, z format. This is the z equals f of x, y format, but we can get to the same point. We can get to the same equation using this. And specifically, we're interested in this at the point 1, 1, 1/2. Okay. Okay, so notice, I mean, I just kind of said this, but notice that this is in the form z equals f of x comma y, right? And, you know, the theorem that we just looked at assumed that f was kind of written in the form f of xyz equals 0, right? And so what we can do here is just kind of a simple, you can notice here that f of x, y minus z is equal to 0, right? And so this guy here is your f of x, y, z, right? And so, but we will have to change, like if we're going to leave the equation in this form and we want to work with the prior theorem, we have to augment it slightly. And so what we need to do is basically rewrite it like this. This is going to be x naught, y naught, right? The partial of f with respect to x evaluated at the point x naught, y naught, and then times x minus x naught plus the partial with respect to y evaluated at the point times y minus y naught. And then because the expression is written as a function, z is written as a function of x and y, what we would do instead here is we would go minus z naught. Okay, right, and then this whole thing is equal to 0. So this is how we would have to kind of augment the previous theorem in order to handle writing the expression in this way. But it's not a problem. You can kind of think to yourself, well, like if I were to differentiate, if I were to find the partial with respect to z, it's obviously going to be, kind of just a 1 here. So this is all hopefully pretty intuitive. Okay, but beyond that, like it's the same setup, right? So the partial with respect to x here, right? This is basically the only term that matters here for this partial is negative 1/10 x squared, and so we know that derivative would be negative 2x over 10, so it'd be negative x over 5, right? And then the partial with respect to y, it's a similar argument, right? You got negative 4/10 y squared, and so when I differentiate that, I get negative 4y over 5. Okay, right, so that's relatively easy. Now can we evaluate these two? So evaluate these at the point 1, 1, 1/2. Well, f sub x at 1, 1 is equal to negative 1/5, and f sub y of 1, 1 is equal to negative 4/5. So that's easy enough. Okay, and now we just have to plug everything in, right? So remember the format here, and I'm going to write it kind of in an extreme shorthand here, is partial with respect to x times x minus x naught plus partial with respect to y times y minus y naught minus z naught equals 0. Okay, so we could plug these all in, and so this is negative 1/5 times x minus 1, right? right? And this is -4/5 times y minus 1, and this is minus z minus a half. And so it looks like that. Okay, and just like before, you could expand this, consolidate terms, simplify terms, etc. But this will be good enough for us. This is going to be the tangent, the equation of the tangent plane to the paraboloid given by this equation here, and specifically at that point. Okay, so similar setup to what we had previously discussed. Similar setup to the previous example. Just different equation, basically. This is an important example to go through because it is written in a slightly different form, and so you have to think about it a little bit differently, but it's pretty easy still. Same kind of idea. Okay, how about, let's go ahead and skip forward here to the next section. So what I'm skipping over here is and I'm not really skipping this. This is a straightforward thing, but finding equations for the normal line to given surfaces. It's a straightforward application of the previous stuff. So what I want to talk about next is another use of the gradient function, and this use is in finding and determining the angle of inclination of a tangent plane. Okay, so another use of the gradient function is to determine the angle of inclination of some tangent plane of the tangent plane to a surface. Well, so what do we mean by angle of inclination? Well, it's kind of, I think it's helpful to just draw a picture, right? So you've got your XYZ coordinate system here as per usual. Right, and you're going to have, so maybe in the course of working on some problem, you've come to identify a particular tangent plane, right? You've got a surface in the XYZ coordinate system, and you've identified a tangent plane, right? And so let's just say, for sake of ease, that it happens to lie like this, right? So you've got, this is the XY plane, and then coming off of that, you've got some surface, right? And we'll say that surface looks like that, right? And so maybe your surface maybe comes and interacts with this, but this is the tangent plane to the surface, right? So this is a plane. So the angle of inclination is going to be the angle that this tangent plane here makes with the XY plane. Okay, and this theta would be between 0 and 2 pi. Pi over 2. Right. Once it hits 90 degrees or pi over 2, then you'd have an angle of inclination on the other side. So that theta never would exceed pi over 2. Okay. So this is what we mean by the angle of inclination. And we can use the gradient to identify this angle. Okay. And so what we have to recall here is the k vector, right? So because the k vector, right, this is the k unit vector, this is going to be normal to the xy plane, right? So because of that, we can use, and let's say, I'm sorry, I should put this on here. We're going to have some vector coming off of this tangent plane, which is what we'll denote by n. And it's normal, right? It's a normal vector, right? This is a right angle with this surface, with this plane. To be careful with my terminology. So this is a plane that happens to be tangent to a surface and happens to have this normal vector coming out of it, right? It's normal vector n. And so because k, so k is just the direction vector, the unit vector in the z direction that we're used to using all the time. K is normal to the xy plane, obviously, that is at a right angle to the xy plane. So because of that, we can use this formula that we previously were using. We've used this formula in previous sections, and the formula looks like this. It's cosine of theta equals, and I think the first time we wrote it like this: n dot k divided by the norm of n times the norm of k. Okay, and then of course k is a unit vector, so the norm is 1 there. And so a better, simpler way to write it is to, acknowledge that fact and leave it off and just write it like this. Okay, and so that is the formula we can use. And so this gives the cosine of the angle between two planes where n is normal to one of the planes and k is normal to the other. And so in our application, n is normal to the tangent plane of interest, and k is obviously normal to the xy plane. Oops, I put a hat on there, I meant to put an arrow. Right, so k is normal to the xy plane, n is normal to the tangent plane, right? And so we can use this slick little formula to identify cosine of theta, and then of course we can use arc cos to find theta. Okay, and so this gives the cosine of the angle between two planes where n and k are normal to said planes. Okay, so this was back from maybe section 5 or 6 of this Calc 3. So, okay, so that's useful. So let's do an example with that. Let's do an example where we make use of this. So let's find the angle of inclination of the tangent plane. Okay, the tangent plane to the ellipsoid given by, right, so you've got this ellipsoid, which is x squared over 12 plus y squared over 12 plus z squared over 3 equal to 1. Okay, so so what we're looking for is the angle of inclination of the tangent plane to the ellipsoid given by this equation, and then specifically at the point 2, 2, 1. Okay, so this kind of wraps it all together. Okay. All right, so first, let's acknowledge what fx, y, z is. So it's this guy minus 1, so it's important. Sometimes it's important. I mean, it's always important to acknowledge that, just because otherwise your understanding isn't proper. But sometimes it doesn't really make a difference with the calculation. But let's acknowledge that this is the actual equation. This is the equation, right? Equals 0. Okay. And then let's find the gradient here. Okay, so the gradient function. It's a vector valued function, right? And basically, how do we identify the gradient? Well, we identify the 3 partial derivatives and use them as the components in a vector valued function with ijk directions, right? So the partial derivative with respect to x is obviously going to just include this term, and it's going to be x over 6. And the partial derivative with respect to y is going to be y over 6. And the partial derivative with respect to z will be 2z over 3. Okay, so there's the gradient. Can we evaluate the gradient at the point 2, 2, 1? Of course. Right, and what do we get? We get 26i plus 26j plus 2/3 k. Okay, and I guess we could simplify this to 1/3 I plus 1/3 j plus 2/3 k. Okay. Okay, so this is the gradient vector, right? And so at this point, the gradient evaluated at 2, 2, 1, specifically this vector, is going to be normal to the tangent plane. Right? This is going to be normal to the tangent plane. And then we also know, of course, from what we've just said, that k is normal to the xy plane. Okay, so let's make sure that we're clear on what we're doing here. So the gradient of f at 2, 2, 1, well, that is equal to the vector 1/3 I plus 1/3 j plus 2/3 k. Okay, and this is normal to the tangent plane. All right, we didn't have to actually find the equation of the tangent plane, but we know that the gradient tells us, the gradient evaluated at the point gives us a normal vector to the tangent plane. And k, of course, we all know, remember what k is. K is just, well, it's 0, 0, 1, basically, or just better written as just k. K is, of course, normal to the xy plane. Okay, and so if we want to know the angle of inclination, we can basically use the equation, the expression, the formula that we just talked through, right? There we said that cos theta will be equal to n dot k, the absolute value of that, divided by the norm of n. Right? So in our case, k is k, and n is this gradient vector here. Right? So this, in our case, would be the gradient of f evaluated at 2, 2, 1. We want to dot that against k, and then we want to identify the norm of that gradient vector and divide by that. All right, like so. And so we can do that, right? We can dot this. So this is the gradient vector, and this is the k vector, right? So obviously, when you dot those together, 1/3 times 0 plus 1/3 times 0 plus 2/3 times 1, the numerator is just 2/3. And then how do we find the norm of this? The norm is just the square of the components. Add them up, take the square root. So it's 1/3 squared plus 1/3 squared plus 2/3 squared. And then we take the square root of that. So that's going to give us the norm of the gradient vector at 2, 2, 1. Okay, and so what do we get here? Well, we get 2/3, and then the bottom it's a ninth plus 4/9. So I guess you get 6/9. The square root of 6/9. And so that's going to be equal to, there's a lot of ways to, well, there's not a lot of ways, but there are various ways to simplify this. This is one way. You can do it this way, and then you'll see that it's 2/3 times 3 over the square root of 6, which is 2 over the square root of 6. And so you could write this as 2 times the square root of 6 over 6. So square root of 6 over 3. Okay. I mean, you could probably write it in other ways too, but then basically the punchline here is that cos theta is equal to the square root of 6 over 3, and that implies then that theta is the arc cos, right, of square root of 6 over 3. Right, and when you do that, you get, like 0.61 radians, right? But probably more useful would be, well, maybe intuitive would be to say that theta is approximately 35 degrees. Okay, so that means the plane that is given right? The plane that is given by this equation right here, the surface that's given by this equation right here has a tangent plane at this point, right? And what we've shown is that that tangent plane has an angle of inclination of 35 degrees, which means that it's rotated off the xy plane 35 degrees. Okay, so obviously very precise and specific kinds of information can now be gathered on surfaces, and specifically because of this gradient function and also directional derivatives in general. And so I think that's where we'll let off. And then the next section we'll get into will be we'll talk about extrema of functions of two variables. So we have the tools now to start talking about relative mins and max and extrema of functions in space, right? So kind of the same sort of idea as what we did in Calculus 2 when we were using derivatives to identify extrema of functions of a single variable. Now we want to be able to do that with functions of more than one independent variable. So anyways, that's where we'll let off, and we will talk to you all next time. Take care.